All right. So we talked about using matrices and determinants to find like the eigenvalues, which were our principal stresses, and our eigenvectors, which was our principal stress directions. So an alternate way that you can find the principal stress directions uh, and the principal and also to do stress transformations is using Mohr's circle. So Mohr's circle is a graphical representation of the state of stress, and it helps avoid complex calculations, and you can use it to to transform a state of stress and find the principal stresses in 2 dimensions. Um, so for a 2D state of stress, if you remember, we had defined the transformation, or to find the normal stresses sigma x prime and sigma y prime, we could use the following 2 equations. Um, so what we're going to do now is we're going to use the following list of trig identities and plug them in to the above equation. Um, and from that we can uh, plug in, for example, for cosine squared theta, we can plug in 1 plus cosine of 2 theta. For sine squared theta, we can plug in 1 minus cosine squared theta. And for sine 2 sine theta cosine theta, we can plug in sine of 2 theta. Okay? If we distribute out all of our normal stresses, what we'll end up getting is the final equation here. Okay? So we can move over our terms. We can move over this one term here, uh, which is the average stress, or the average of the 2 normal stresses. We can move it to the other side. All right, and we can leave it at that. Okay. So we can also rearrange equation number 2 here, and we can write it as being equal to tau is going to be equal to minus the difference between the two times sine of 2 theta plus tau xy cosine of 2 theta. The derivation, I left out the derivation, but you can use the trig identities to determine that as well. Okay, so um, so if we have that, all of that, what we can do is we can add. So if we take both sides of equation 5 and equation 4 and we square them and then add them together, what we end up getting is we end up getting this long equation here. All right, but a lot of the terms cancel each other out, so um, what we end up getting is just this final equation, equation 6 here. Okay, so the cool thing about equation 6 is if you say that if we treat sigma as being on our x-axis, and we treat, if we think of tau or shear stress as being our y-axis, it ends up looking, this equation looks exactly like a circle, where our x offset of the center of our circle is equal to a, or in this case it's equal to our average stress, sigma x plus sigma y divided by 2. And then our b-intercept is equal to 0, because there's no intercept related to tau. And then our term on the right-hand side of the equation is our radius of our circle squared. Okay, so what we can do is we can follow this following procedure to to um, to draw our Mohr circle. Okay, so we're just going to follow our procedure to draw the Mohr circle. So first step is we're going to draw the center of the circle. So the center of the circle here is going to be at um, the average, which is going to be equal to sigma x. The average of our normal stress is sigma x plus sigma y divided by 2, and then the y coordinate will always be 0. The second thing we're going to do is we're going to draw our radius of our circle. So the radius of our circle is going to be equal to the square root of sigma x minus sigma y over 2 squared plus tau xy squared. All right, tau x. So what we could then do here is we would have draw our circle offset by a radius r from our center. Okay. The third step we would follow would be to locate the x-intercepts of your circle. These are your principal stresses. All right. So this where it intercepts the x-axis at these 2 points. Those are our two principal stresses. This is sigma p1 and this is sigma p2. All right, so sigma p1 is going to be greater than sigma p2. All right, and then our fourth step is going to be to plot the state of stress. So if we were started off with our state of stress as being sigma x, sigma y, tau xy, here, all right, we're going to have 2 points, which I'm going to call point P here, which represents sigma x and tau xy. All right, so the one thing I will note about the Mohr circle that I didn't note earlier is that the x-axis, the positive direction, is along the traditional, I guess, like positive x direction, and the negative direction is this way. But for the shear stresses, well, our convention will be that we'll draw positive shear stresses going along the negative y-axis, and negative shear stresses going along the positive y-axis. So that's something I really want to emphasize. The reason we do this is it then allows our stress transformation, when we do our rotations for our stress transformations, the angles will follow the correct direction. So a clockwise rotation in this space will match a clockwise rotation in the normal xy plane here. Okay, so this is for this state of stress, we can plot point P, which you can think of as being like the right-hand side of this element, and then on the opposite side of the element, or 90 degrees apart, 180 degrees apart, will be the state of stress for sigma y, and then the negative value of the shear stress acting on that plane. So that would be, we'll call that point Q. Okay. So the last step is that you can transform the state of stress to any other state of stress that you're interested in by rotating it by a given angle, theta. So let's say we had so if we wanted to go from the xy coordinate system to the x prime y prime coordinate system, all we have to do here is so let's say our xy coordinate system was like this, and let's say our x prime y prime coordinate system was separated by some angle theta. All we have to do is, on the Mohr circle, is we have to rotate 2 theta on it. So what we're going to do is we're going to take this equivalent state of stress, we're going to rotate it by an angle 2 theta, and we'll get a new state of stress, which will be P prime and Q prime. All right? Which is represented by this line here. So our new state of stress would be like this. We would have our sigma x prime, our sigma y prime, and our tau x prime y prime. We could get all those values from our Mohr circle at points P prime and Q prime. So at points P prime, we could get sigma x prime and tau x prime y prime, and at point Q, prime, we could get sigma y prime, and also the negative value of tau x prime y prime. Okay, so this is how you can use the Mohr circle to calculate um, the principal stresses, as well as perform any state of stress, or calculate any state of stress um, that you'd need, um, uh, I guess, between 0 and 90 degrees, or 0 and 180 degrees. Sorry.